Okay, quiet please. Right, and there's going to be these U tries for you to do. Okay? Quiet please. Come on, we want to get done with this quickly. Yes. Okay, we could just stretch this out the whole block if you want. I'm trying to get it done in 10 minutes, right? 15. Maybe 20. I mean, this looks like a lot of stuff, but truthfully, it's all the stuff we've already done before for other kinds of functions, which is, right, we learned in 2 sections ago about compositions. We learned about compositions so that we could understand inverses. We learned about inverses so that we can understand that radical functions are inverses of quadratic functions. And that was the whole point of that. And that means that the graphs of radical functions have to be flips across the line y equals x of a parabola. Right? So that's the basics of what do we know about the graph of a radical function. If you take a parabola, specifically like the last homework, if you take half of a parabola and you flip it across the line y equals x, that's what the graph of a square root anyways, looks like. And that's why they presented it this order, 6, 6, 6, 7, 6, 8. Right, so here was the graph of, this is the half of parabola right there, and if I flip it across the line y equals x, it looks like this. So if I take away the other two and just look at the square root, that's what a square root function looks like. That's the parent function of a square root. So I can write it like, oops, don't like that. Edit, undo. Y is the square root of x. That's the parent function. And we know the domain of it has to be x is greater than or equal to 0 because you can't take the square root of a negative. And we know the range of it is y greater than or equal to 0 because we assume the radical is positive. So we really are going to have to start looking at these and saying that, domain is x greater than or equal to 0, range y greater than or equal to 0. Okay, so once we know that, we're going to learn how to graph these things by doing the same kind of transformational approach that we did already with absolute values and parabolas, where you just move them around with the numbers that you've added or subtracted inside or outside. If you remember when we did these before, and I just using the radical right away, what did it do to the graph of a function when you subtracted inside the function? Was it up, down, left, or right? Right. Inside the function, minus means right. Okay. What did it do to the function when you added a number after the function? Up. Okay. What did it do to the graph when you put a minus in front of it? Flip. What did it do when you added inside the function? Left. And subtract after the function means down. So that's how it worked with the other functions. That's how it works with all functions, including this one too. We're not trying to learn anything. There's nothing new about that part of it. The only thing that's different is the parent function, the shape of the parent function. So you'll see here how fast we can get through these slides when you're ready. Richard, ready? Okay, so sketch the graph. Y equals the square root of x plus 2. Which way does this graph move? Holy mackerel. We just did this stuff, right? After the function, what does it do? Up, okay? So this is the up, right? So the graph, and this is my magic here, right? The graph, oops, is up 2. That's it. You just take the original function, scoot it up exactly to done. We're not looking to plot points. We're just looking to kind of know what we know about the parent function and how that number changes the graph, scoot it up to. Okay. Try this one. What's going to do to the graph? Okay. This is going to be down 3. So take that graph and move it down. I can't see. 3. Done. Transformational approach. When you sketch it, just make your tick marks and do your best. I mean, there is some graph paper. I doubt I have enough graph paper for all classes all day, but I want to use what you got. That's fine. Okay, what about, then the next one is you try. So try to do the same thing for those 4. This is the first you try. Just sketch them all, right? Sketch them all. You can do them all on the same background if you want. What's that? Yeah, put it on a separate piece of paper for your you try. Okay, the wrong thing. So what was that one? That should have been up 1. Does everybody get that? Yes. Okay. And the next one was a down 2. Easy, right? The next one is a down 4. And this one, I've grid's a little different, but say it's -2, -4, so it is down 4. And the last one is a up 5. Up 5, right? So that's what the 4 of them should have looked like. Okay, now, how are we going to shift that graph? Left 4, right? Plus, inside plus means left. So left 4 makes it right about there. Okay, what about that one? Right 1. So grab the graph. 1, go. Right 1. Good. Everybody all right with that? Left and right. Plus means left, minus means right. All right, so try those 4. So what kind of shift is that first one? Right. Okay. So let's grab that. There we go. And go right 3. I can't see. 3. About right there. How about the next one? Left 1. Left 1. Done. How about the next one? Left 6. That looks good. And how about that one? Right. And that one will look like this. Boom. About right like that. Okay. So that was up, down, left, and right. We did all that. This one is one that we don't see a lot of, but what happens to a graph when you multiply it by a number? If I multiply it by a number bigger than 1, what do we call that? I mean, it's literally, if I made a table of values, right? X, Y. I mean, if I put in x equals 0, I still get 0. If I put in x equals 1, now the value of the function is, it's not 1, it's 2 times 1, it's 2, right? If I put in, let's say, 4, the square root of 4 is 2, and times 2 makes 4. So actually, if you come over here, right, it's x is 1, y is 2, x is 4, y is 4. It's actually making the graph go up faster. It's called a stretch. So let me draw that. In fact, I can do that in a different color. Is that on the pen? Yeah. That is called a stretch. Like if you multiply by a number which was less than 1, then it would go up slower. That would be called a compression. I think they're calling it compression this year. Used to be a shrink. Now it's a compression. So try to do the same thing with that. And you may just have to kind of estimate a little bit. I mean, if you're making your table of values, blue, good. Right, make a table of values with the same 3 numbers, x, y, 0, 1, and 4. Mine is not even going to fit it on there, but. What would be the value of the function when x is 0? 0. That looks like a heart. Crazy. 0. What's the value of the function when x equals 1? 3. How about when it equals 4? 6. So I don't even have the right things on here, right? So 0, 0, 1, 3, right? It's going up. It's stretched by a factor of 3. And 4 goes up, and it's way up here somewhere. So there's the graph. Okay, let's see. What 2 things are going on in this one? Okay. So this minus means flip. And the -1 means it's outside the function, so it's down, right? So we're going to take this thing here. I think I can do this, right? And I'm gonna turn it. Oh, does it let me do that? Yeah, it's not right though. It's not the way it flips, is it? I'll just do it in a different color. Red, and fat. So down one, and flipped. So it would look like this. Right? Down one and flipped. Good? So try to do the same thing. This time it's minus outside again, but it's -1 inside, which means sketch a graph. Oh, that's not what I want. So then the graph goes, it's flipped, so it should be here and here. Not on the pen, that's why it wasn't working. And it should be here and somewhere out there. So it's like that. Right one and flip. You get it? You understand the shifts, the flips? Okay. Now there is one other, most everything they ever give us is square roots, but it could be cube roots. Cubics, polynomials, and cubed roots are part of this. Let's get that back to blue. The cubic function looks something like this. There's a little bit of a wiggle in the middle like that. It goes through 0, 0, and like that. If you flip it, it looks like this. We had in a benchmark a couple of years ago from downtown, they had a graph of that function, and they said, what kind of function is it? And they said cubic, and that was wrong. That's cubic. That was cubed root. That happens sometimes. So these, what is that? They're inverses of each other, right? If you cube something or if you take the cube root, they undo each other. So they're inverses. So their graph should be flips across the line. That's what a cube root function looks like. If you wanted to transform it, everything else works the same. You're just starting with this basic shape. Right, so what kind of transformations am I doing in this one right here? Left and down. So I'm going to grab this function there. Now I'm going to go left 2 and down 1. So it's about right there. Done. It's the square root is so much cleaner, than this thing is. This is always a harder one to actually see. And I think the chances of you seeing it, like on a benchmark or SOL, not great. I mean, definitely the square root is the one you really got to know. Everybody got it? That is it. And you just did the homework. That was the U tries. So you're done, okay? So if you want to hand them up, you're